So let's look in a bit more detail at conjugate points, extremals and envelopes. Now you've seen the idea of an envelope in the previous video whenever we looked at the projectile motion, which produced a set of parabolas and those generated an envelope. Now we can write the solution to the Euler-Lagrange equation in this general form. So if you look at the previous course when we worked through lots of examples, you'll see in those examples the final solution is for the extremal is given in this kind of standard form. So it's a function of x and two parameters c1 and c2. Now if we want to, we can create another extremal just by adding on another variation. So this is the original extremal and we'll add on this little variation here, alpha u of x. So there's nothing new in that. You've seen this whenever we derived the second variation and we had one variation and we added on a second variation given by our alpha u of x. But we know that then looking at this thing here, whenever this function u of x is equal to 0, we're just back to our original extremum. Now we know that u of x is going to vanish at some point a, so we can say u of a equals 0. But we also know then that u of x will vanish at all the points conjugate to a, so that's the a dash. And we've seen that previously, so in case of the sphere, we have the value of a and a dash, so the u of x would be 0 at a and also at a dash. And the same in this instance here when it came to the projectile, u of x will be 0 at a and it will be 0 at all of these points here, which are the a dash, which are the conjugate points, which in this case map out an envelope. So that's what we talked about in the previous video. Now let's note that we don't need to add the variation on like this here where we add on the alpha u of x. We could write the variation in terms of a delta c1. So in effect the variation has been added on to the parameter c1. You could also add it on to the parameter c2. So it means that we can then write the value partial y by partial c1 times delta c1 would give you the total variation of our value of y, or the total change in the value of y. But we've already seen in a previous video that delta y upon delta c1 is going to be one of the solutions u of x of the Jacobi accessory equation. So it means then that if this delta y upon delta c1, which is u of x, vanishes at a, it also vanishes at all the points which are conjugate to a. So it means that when the equations 1 and 2 above, that's these two equations, which is the original extremum and the second extremum here, so this is the original extremum with a variation added on, when both of those intersect, if they intersect at point a, then they're going to intersect at all points which are conjugate to a. So this means that the conjugates of a are going to be the limiting points of the neighbouring extremals which are passing through a, and they're going to form an envelope of extremals. So let's go ahead and we'll have a wee look at that again in the graphical calculator. So if you get into Desmos, again you'll find the file which you can open up and it will show you this simulation here. Again, this is the projectile motion which will create parabolas, and we imagined we had a cannon at the centre here and firing a cannonball up into the air. So you can see if we were to pick two neighbouring extremals, so this is a one extremal here and the next extremal. So if you like, this one here is our s of the function x, c1 and c2, and this is going to be the next one, which will be s of x, c1, c2 plus alpha u of x. And again, whenever the alpha u of x is equal to 0, then this one here will just tend towards this one here. But what we're looking at is a limiting factor, and the envelope is going to be the limiting factor of these two extremals. And we can see that actually here because the little red dot is covering it along the extremals. So what we can do is we can add more and more extremals in between each of these. So let's go ahead and we'll add a few and we'll get the envelope so it looks a bit more detailed. So if I come down here, let's to actually this point here. So to either change this for 0.1 and we could change it to 0.05. And you can see that straight away we've got the intermediate extremal appeared here, and we can zoom in there. And again, we can keep doing this, so I could put in obviously the value 0.01, and we're getting more finer detail. So this is really what we're saying about the limiting factor of the two extremals is going to generate this envelope. And I'll just zoom out and we can see that in all the glorious detail. So you can see the envelope appearing and it's a lot more pronounced. Take a second for it to render here. So there you go. So that's given us a good graphical representations of the fact that the conjugates of the point A are going to be the limiting points of neighbouring extremals. That's as the extremals get closer and closer together, and they're going to form an envelope of extremals. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.